National Television of Ohio, Incorporated.
How do you do, ladies and gentlemen, and boys and girls? I'm Julius Sumner Miller, and physics is my business, and the physics today has uncommon enchantment and beauty. It has to do with soap bubbles and soap films and surface tension and why raindrops are round and other such enchanting matters. Let me do now, first on the blackboard, some introduction to the first experiment, which you will be enchanted by, I am sure. Let us consider a T-tube, so, with an arm here, and a little funnel or thistle tube there, and a thistle tube here, and let's say a rubber tube there, so I can blow some air in here by mouth. Now I am going to dip the ends of these funnels into some soap solution and blow some bubbles. So you see what has come to me in my 58th year, an old man, a physicist, playing with soap bubbles. But I have spent 40 years playing with soap bubbles and have not yet tired of it. So I'm going to blow two bubbles. Now I could blow two bubbles, both the same size, but there would be no interest in that because there'd be no problem. I like to pose problems. So I am going to blow a small bubble on this side and a big one on this side. S for small and B for big. And I can do that because some of the tubing here is flexible and I can shut it off and blow more air into that one than into this one. Now, having blown the two bubbles, I close off this connection with the outside atmosphere. So the bubbles are connected with each other, but not with the outside air. And the logical question that must be asked is this: what now happens? And invariably, everybody says, well, they get equal, because there's more stuff in here that comes over here, and when they get equal, there's the same stuff in both, and then they stay equal. But this is not so. It turns out that the smaller bubble blows the bigger one bigger. As one student once said to me, it looks, Professor, as them that has gets, which is a very good expression of it. Why does this happen? Well, the fact remains that the pressure in the smaller bubble is greater than in the bigger bubble, which ravages reason. Now let me do this. I have here the two little funnels, and here is a soap solution, and there is soap. And I squeeze here. And now I shut off the connection with the outside air and watch the smaller bubble get smaller. Watch it. We're a little twisted there. Watch it. Look at it. Look at it. And not only does it get smaller, but the smaller it gets, the faster it gets smaller. Watch it. Watch it. Watch it. Watch it. Look at that. Look at that. I'm going to blow it again. Watch it now. And I would call your attention to the beautiful colors in the soap bubbles, which has to do with the colors. There it is. Look at it, getting smaller and smaller, smaller. And this is well, it's incredible that the smaller bubble should blow the bigger one bigger. And for those of you who are equipped with the mathematics, the pressure is inversely as the radius of the bubble. So we are dealing here with pressures in bubbles. 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 B-U-B-B-L-E-S. Now, bubbles is one kind of business, and drops are quite another. So I'm going to show you some wonderful experiments, first with surface tension on a liquid, and then on the shape of droplets. Consider the following. I have here a little paper cup, which already has some water in it, and I'm going to pour more water into it. More water. More water. And I hope you see that the surface is quite rounded up, quite much higher than the cup. Look at that. Isn't that incredible? Incredible. Notice how much above the cup that surface of the liquid is. Indeed, let me go back and make a comment about that. I have sometimes had a vessel filled with water so that it overhangs like that. And this surface film has great tenacity. Indeed, have you not seen little bugs flitter about on the surface of a quiet pool of water without getting their feet wet? Now, I'm going to show you that on this high elevated surface of water, the membrane surface is so tight that I can float steel on it. And here is a needle which is steel. And I'm going to try to drop it on there and hope to show you that steel can float on water. Watch it now. I must be very careful because I may puncture the surface film and it'll sink. There it is, there it is. Oh, man, am I delighted. There is the needle floating on the water. Steel floating on water, which shows you the tremendous tenacity. Now I spoke about droplets. Here I have some mercury and a medicine dropper, and I am going to take out some mercury and form a drop. And look it, when the drop is small, it is round, spherical. But the bigger it gets, oh, I have a little water mixed up with that, unfortunately. But you notice that the bigger the droplet gets, the flatter it gets. But the point I wish to make here is as follows. Supposing I bring two droplets of mercury close upon each other. Oh, I mixed this with a little water, which spoiled the effect somewhat. But supposing I bring them close upon each other. Watch them, watch them. Oh, look at that. Look at that. Well, as a matter of fact, the fact that I got the mercury a little wet with water has changed the surface tension properties, and it is not doing what I want it to do. Indeed, it is doing just what I don't want it to do, which raises some very exciting questions. But the point I wish to make is that when the drops coalesce, go together, they go together with enormous forces and speed, and this is due to the electrical properties which the liquid possesses. So there we have surface tension, the shape of drops, and the shape and form of bubbles. And while I'm on this, I would suggest to you that there is a paperback book entitled Soap Bubbles and the Forces Which Form Them, written by an English physicist whose name was C.V. Boys, B-O-Y-S, like boys and girls. And I would urge you to read it because there are hundreds of experiments there you can do with soap solutions, soap bubbles. Now more on the same. Here is a rectangular cubical frame of wire. I'm going to submerge it into the soap solution and withdraw it, and you notice the enchanting shape which we have here. Now, what must physicists say of these shapes? The shape which the soap has taken is a shape of least energy. And you will remember on an earlier program I remarked that the energy of a system tends toward less. So watch what happens when I puncture one frame. Watch. Oh, there it goes, and look at that beautiful shape. And now, there it goes. There it goes. Oh, there's another one. Always tending toward a surface of less energy. Now, why are raindrops round? The reason they are round is that they have the largest volume with the least surface. That's the property of a sphere, and hence their energy in this shape is the least. To show you that a circular or spherical form is always that toward which a system goes, I'm going to dip this ring in some soap, and here is a flexible loop of thread. Now watch what happens. I draw it out, and I have, oh, it's not what I want. I draw it out. Oh, it's not what I want. Oh, well, I'll show it to you. Do you see that the curvature of this thread is circular? Let me try it with another one. I thought I had, oh yes, here's another one. Let me try it, because there are some problems in doing, oh, yeah, this is all right. Now, I'm going to puncture one film and watch the action, the motion of the string. Oh, there it is, into the arc of a circle. So the film above tends by contraction to a least energy. Further proof of this, here is another ring, and here is a closed loop in here, a closed loop. I'm going to dip this into soap solution, withdraw it very carefully, and you see the loop inside is quite closed because of the tenacious holding of the soap film. Now I'm going to puncture the soap film in that little ring, in that little loop, and you will see it all go into a circular arc. Watch it, watch it. There it is. Now let me do the break the film elsewhere in the larger part. Watch it, watch it. There it is, tending toward least energy. I'll do that once more because it's quite enchanting. Watch it. Oh, look at, oh, did you see how tenacious that soap film is? Now watch it. There it is. It goes into the arc of a circle. Here are two loops, side by side, and some interesting things can be done with them. Oh, I'm having a little trouble, and I may abandon it. Yes, let me suggest what you would witness. Let me suggest, because it's very important. Supposing you took a funnel and another funnel, and you dipped their front edges into soap and brought their faces together close and then separated them. What would you have? Well, the film would have that curvature, and that has a very special kind of geometry. That is called a catenary, C-A-T-E-N-A-R-Y, and that's the Latin word for chain. And indeed, if I took a chain here and held one end so and one end so, the curvature of that chain would be a catenary. And it is interesting to discover that in this shape, that film surface has the least energy, which is a fundamental principle of nature, that the energy of a system goes downhill. Now, since I am interested in blowing soap bubbles, I have here something I'm sure many are familiar with, a little pie plate with some soap solution and a ring, and there, there I make some bubbles. And I call to your attention their beautiful property. They are spherical. Oh, I thought I could catch that. Watch it now. Oh, I may be a little too impulsive. There it is, there it is. Watch it, watch it, watch it. Oh, I caught it, and it went through the other one, which suggests the tenacity of this business. Look at that. Now, what has this to do with other important matters in nature? I already said that raindrops are spherical, very important. And indeed, may I suggest, if you have a clothesline that hangs from here to here, the next time it rains, I urge you to look carefully at the raindrops that are hanging, the water drops that are hanging. They hang very, very sharply formed and all spherical. And now what do you see happen? These which are in a higher potential level slide downhill. This one hits that one, they coalesce and get bigger, and now the surface tension force is not adequate to hold up this greater weight, and it drops down. So here is a beautiful thing to witness. One last thing. Here is a wedge-shaped vessel, one of which, now held in my right hand, has water in it that is colored with food coloring, and the other has mercury in it. And I hope you see a very distinguishing feature. Let me show you quickly what that feature is. If I have a narrow tube immersed in water, the surface in the water would be so, and the upper surface in the tube would be so. In the mercury, the surface would be so. And this is very important for the affairs of nature, and I thank you for your attention. How do you do, ladies and gentlemen, and boys and girls? I'm Julius Sumner Miller, and physics is my business. And our business today has more than ordinary enchantment, and I will go at once to it. Consider the following. I have a tin can with some water in it, under which I have put a burner, so that the water has now been boiling for a time, as evidenced by the water vapor seen here condensed, and we call it steam, so that what remains in the vessel now is some water, less than before, and some water vapor. Now I'm going to take the burner away and stopper up the can, and we will witness an astonishing and absolutely astonishing thing. If we listen very carefully, we will hear a certain flexing of the can. What is happening? Some of the water vapor is condensing, the pressure is getting less in the can, and the atmosphere is taking hold. And atmospheric pressure is an astonishing thing. I will hasten the process by pouring some cold water on it. And this is an experiment you can do with absolute enchantment yourself. Here it is. I am going to take the burner away. I am going to stopper this up. I'm going to put it down here. Listen. Oh. But watch it. I'll hasten the process. Oh, there it is. Let me turn it around. There it is. And I say that is something to bear witness to. That is fantastic. The push of the air, staggering in its consequences for the human race. Now listen. The water is boiling inside that can at reduced pressure, at a much lower temperature than 100 degrees centigrade, because the pressure inside is less than 1 atmosphere. This is fantastic. Fantastic. Let me show it to you another way. Here I have another tin can, and I'm going to connect this tin can to a vacuum pump, which permits me to pump out some of the air, and just a little of it. I could never pump it all out. If I pumped for 1,000,000 years, I couldn't get it all out. Why? Too many molecules in there. But let me... There it is. There it is. There it is. The push of the air. Staggering to witness. Staggering. Show it to you another way. Take a look at another piece of apparatus. I have a funnel. A funnel. And across the top of it is a sheet of rubber tubing, as from an automobile inner tubing. The air inside is at atmospheric pressure. I'm going to connect the vacuum pump here and reduce the pressure inside from atmospheric less and less and less and less. And the rubber sheet, suffering the forces, the push of the air, will be depressed inside deeper and deeper and deeper. And indeed, if it can endure the reduction in pressure and the push of the atmosphere, I shall be surprised. Very likely, it will be torn apart. Here it is. There's the rubber tube. I am going to connect this. Now, I'm going to reduce the pressure. There it is, getting pushed in. There it is, getting pushed in. Oh, man, this is something. I'm going to stop it a minute. Let's get a tight shot, if you will, of that. And notice the enormous push of the atmosphere. Fantastic. Now, I'm going to evacuate more and more and let the push of the air push that more and more. And I'm going to step aside, because when this does indeed burst, it has a detonation which could, well, unseat this building. That'd be very good. Oh, I like to do this once in a while because it adds to the drama of the matter. It adds to the drama. Oh, there it went. There it went. I hadn't expected it, really. But notice the enormous forces of the air. How enormous? Well, only about 15 pounds per square inch at sea level. Let me remind you of the consequences. The ordinary human being has about 3,000 square inches of surface. 3,000 square inches of surface. 3,000 square inches. If you skinned an ordinary human being, laid out the skin and measured the projected area, it'd be about that. On every square inch, there's about 15 pounds. 45,000 pounds is the push of the air on me. Over 20 tons. Is there any wonder why at the end of the day a fellow goes around all worn out, carrying that load of air? Now, to show you further the consequences, consider these things, which we need to look at sharply, acutely, circumspectly, because what is said about them is always wrong. They are called suction cups. Suction cups. And I must advise you to put the word suction out of your vocabulary. It is unacceptable. Why? Because there is no suction, no such force. What do? Let me squeeze them together, face upon face, and what have I done? I have squeezed the air out from between them. Now, why are they held together? They are held together because of the push of the air. I could compute it very readily. If, let us say, I have squeezed out all the air inside from between them, all I need to do is measure their area. Pi r square is the area of a circle. And that area in square inches times 15 pounds per square inch. Indeed, it turns out that about 300 pounds is necessary to pull these apart. There, about 300 pounds necessary to pull them apart. Of course, look at the usefulness. Look at that. Indeed, regarding the usefulness, the next time you watch people who change big panes of glass in department store windows, you will notice the pane of glass weighs half a ton and 3-4 men carry it. How? By fixing a so-called, forgive me for the use of the language, so-called suction cups, and then they carry it around. The push of the atmosphere. Now, I used a vacuum pump in this, and you should read about Otto von Guericke, Guericke, who in the 16th century invented the vacuum pump. And I want to show you his first one, if we can get a tight shot of that. There we are. Notice, here is a pump with a piston and 2 men are drawing on it, and he reports in his report to the societies, the scientific societies, that there was first a slight hissing as by bees and birds, and then bang, the cask collapsed. Here is another one showing the same. Fantastic. Those 2 hemispheres put together, the original Magdeburg hemispheres. And here is a picture of von Guericke. So we should pay him tribute. We should pay him tribute. Now, I have spoke of the Magdeburg hemispheres. Let's take a look at them. Here they are in replica, 2 hemispheres made of steel, which I put closely face to face, and then I connect the vacuum pump, and the valve is open, and I take out some of the air. I take out some. Never all, could never take it all out. Then I'm going to close the valve, shut off the pump. Now I'm going to try to pull them apart. Never, not 1 man alone, indeed 2 could hardly do it. So I'm going to do something. Obviously, the pressure inside is too low. The push of the atmosphere outside is too big. I'm going to do something. Watch, listen. I'm going to open the valve instantaneously. There. Now what did I do? Oh, some say you let some of the vacuum out. Oh, that murders me. As Macbeth doth murder sleep. Didn't let any of the vacuum out. I let some air in. Still too much. Let more of the vacuum out. Oh, now I let so much out that all of it's out. And so we have the Magdeburg hemispheres, a classical demonstration, historically, of atmospheric pressure. One more very dramatic one. On an earlier program, I showed this when I talked about inertia. But I want to do this now because it is a demonstration of atmospheric pressure. You see, ladies and gentlemen and boys and girls, what I'm trying to do is not teach any physics in these recitations, but rather stir your interest by events which are dramatic for the soul. Here is a sheet of paper, about 20 inches one way and 30 the other, 600 square inches. On each square inch, 15 pounds of air. 600 times 15, 9,000 pounds of air. And you know, as I did before, I'll do it once again. I cannot move the weight of that air. There it is. And I say that is staggering to contemplate, the push of the air. Of what usefulness is this? Oh, well, without air, birds couldn't fly and airplanes couldn't fly. Indeed, talking about flying, here is an instrument called an altimeter or an altimeter. What does it consist of? It consists of a little chamber which is highly evacuated. I'll try and draw that little chamber which is highly evacuated. Here it is. Highly evacuated, and it has a lever system on it with a scale. Now, if we go high into the atmosphere, the air inside expands a little, the cover lifts up and pushes the lever down, so we get a reading of the altitude in terms of the pressure of the air. Or, if you wish, another use made of the atmosphere, which has so much to do with the events of weather. Here is an aneroid barometer, which has inside it exactly the same thing. The response of the chamber to increase and diminution of pressure gives rise to a reading, and I invite you to look up the word aneroid, because what does it mean? It means without, a meaning not, and neros, wet, without wetness, so it is not a mercury in glass barometer, but a dry barometer. And talking about a mercury in glass barometer, here's something you can do. Take a long glass tube about 1 meter long and fill it with mercury. It's closed at one end, fill it with mercury. Then take a vessel in which some mercury resides, turn the tube upside down, of course with your finger across the open end, submerge the open end in this vessel of mercury, and take your finger away. Remember, the tube is filled with mercury. What would you expect? You would expect all the mercury to fall out. No, it does not. It falls to a certain level, and notice the shape of the meniscus, the shape of the surface. It falls how far? So that this length is about 76 centimeters, or about 30 inches. And that is one atmosphere which sustains this column of mercury. And here is a region highly, highly empty of everything, except a little mercury vapor, perhaps. So one of the best vacuums we can get is produced by such a performance of a mercury column in a glass tube. Now let's see what else we could show. What else could we? Look at this. Isn't this fantastic? Indeed. Oh, I have another one. And since it enchants me, I'm going to do it. This was boiling over there. Here it is. Notice. I'm in a hurry. Listen. There it goes. Notice, I thought I had not boiled the water long enough, because if there was any occluded air in there, we would have trouble. And so, are you not agreed that atmospheric pressure is a staggering thing to witness? And I thank you for listening. How do you do, ladies and gentlemen, and boys and girls? I'm Julius Sumner Miller, and physics is my business. And our very special business today is a very important subject, which is commonly referred to as centrifugal force. Centrifugal force. And I'm going to put the word centrifugal in quotation marks, because it is so badly, falsely, erroneously, incessantly badly used. Illustration. Here I have a ball on a string, and I whirl it in a vertical circle. If now at the top of the path, let us say, or at the bottom of the path, I let it go, I cut the string, does the ball go radially outward from the circle? No, it does not. It goes tangent to the circle at the place in question, like that. I'll show you that letting it go at the top. So, I point out by this argument that there is no force radially outward on the ball, a notion which is often badly used. Now, as an illustration of what I mean, here I have a little chamber in circular trough, tube, in which reside two spheres, and they lie at the bottom here. Question, I want to get one up that end, and I want to get the other up that end simultaneously. How do I do it? Obviously spin it about a central vertical axis, and there they go. Now it is commonly said that centrifugal force drove them out. But since this is not intended to be a lesson in physics, I can only say that that argument, that notion is quite wrong, as we will see in subsequent demonstrations. There is indeed a little toy connected with this, and I would have you see it, because it's quite enchanting for beginners to learn about the forces involved here. Here is a little circular trough, a toy indeed, in which reside two spheres, as in the bigger apparatus I used, and you will see that they lie one on each side of a partition. Question, I want to get one into a recess on one end of the tube and the other into a recess on the other end of the tube simultaneously. Solution, and when you play with your classmates with this, if one doesn't know it, you can always turn your back and surreptitiously, sort of secretly, spin it. I'm having a little trouble, but that is the way nature. There I have it, and each resides in its own little chamber at the ends of the trough. Now, I showed you in this demonstration that the spheres went outward. I now want to do a very classic thing, which raises an interesting paradox. I have here another rotating mechanism. On this end, there is a candle which I'm going to light. And I put a little chimney around it to protect the candle. And on this end, there is another candle which I'm going to light. And I put a chimney around it to protect it. And now I am going to rotate this system about a central axis. And the question to be asked is, what do the candle flames do? Well, there are many possible things the candle flames could do. They could lean out. They could lag behind. They could lean in. They could lean out and back, which is sort of diagonally. They could do many things. But the reason I call this my candle paradox is that they do what is least expected. Watch, and we shall see them lean in. Watch it. They are leaning in. They are leaning in, which is an amazing thing. Regarding this fictitional centrifugal force, supposing we had some water in this bucket. You know, one of the classics of all time, you can swing the bucket in a vertical circle and the water will not come out. Question, in the case of the ball on the string, whatever I did with that, oh, it's gone. If I swung the ball too slowly in a vertical circle, is it not true that at the top of the path, here I have it, and I'm going to show you, is it not true that if I am not going fast enough, the ball won't make the circle, it'll fall down? Question, supposing I have some water in this bucket, and I do this with it, and I don't go fast enough at the top, will the water fall out of the bucket? Nearly everybody says yes, but that's not true. Answer why. When the bucket is up here, and the water is starting to fall down, the bucket falls down at the same rate. So the water does not come out of the bucket. So you see, this is an old fable, very falsely treated. Consider some more of the same. I have here two vertical steel hoops, which are fixed on the bottom, but free to move on the top of the central shaft. And I'm going to put these into a rotator, which permits me to spin the thing fast about a vertical axis. And I want you to see what happens. And we could then very reasonably say, this is why the Earth is flattened at the poles. Watch it. I'm going to speed up the rotational speed about the vertical axis. Now, the consequences of the Earth's rotation on its own axis, about 1,000 miles per hour at the equator, because doesn't a point on the equator go 24,000 miles, 25,000 miles around in 24 hours? There is much consequence to this. Persons weigh less at the equator than they do at the poles for two reasons, both of which I'll leave to you to explore. Consider another consequence of this high-speed rotation. Here is a thing called a governor. There is a sleeve here on a vertical shaft, and if I spin this system fast enough, you know what will happen. The spheres will move in this fashion. The sleeve will move up on the central shaft, and it could well intercept a valve here, which would shut off fuel to the motor, and that's why it is called a governor. Oh, notice I'm pretty nearly on dead center. There it is, there it is, there it is, there it is, a governor. Here is one that you can do, utilizing this fictitious force of centrifugal stuff. Here is a coat hanger, and here is a coin, a penny, the lowest coin of the kingdom, I guess, and I'm going to put that coin at rest on the bottom part of the hanger, and I'm going to swing this hanger with the coin on it in a vertical circle, and I say I can keep the coin there. Why? The coat hanger will exert a force on the coin just as the string exerted a force on the ball to keep it moving in a vertical circle. Watch it now. Somebody says, well, I hope it doesn't work, Professor, because, you know, well, if it doesn't work, then I've lost my professional dignity, but there must be a reason why it doesn't work if it doesn't. And remember, we don't ever say that the experiment failed. Watch it. Oh, it did go around 2 or 3 times and then flew off. Let us consider now another classic, which is really quite astonishing. Here is a glass tube through which a string passes. And I have named this demonstration the string in the glass tube. Notice the elegance of that. A string in a glass tube, I've named it the string in the glass tube. Now here on this end of the string is a little 10-gram weight, and here on this end of the string is a 100-gram weight. Now you know that 10 grams can't hold up 100. Of course not. 10 cannot hold up 100. But I'm going to do something to the little one and thus give birth to a strange force which will hold up the 100. Watch it. There we are. There we are. The 10 is holding up the 100. Indeed, I'm going to make it lift the 100. There it is. Oh, I'll do it again. There it is, lifting it. Now, we must never say that there is a force radially outward on this thing pulling on the string. Oh, wait a minute. I said something wrong, and I'm glad I did, because it may lead some of you to catch me up on it. I said there is no force radially outward pulling on the string. Yes, yes, yes. There is a force which the string exerts on the body, and there is a force which the body exerts on the string, but there is no force radially outward on the body. So you see, ladies and gentlemen and boys and girls, in the heat of this argument, I could very well make an utterance which the good people will quickly detect. And I'm glad I detected it, so you will see that there are occasions when I say things that are not right. Consider another of this business called centrifugal force. Here is a flexible loop which happens to be of rubber. I sometimes use a chain. Very flexible. It hangs quite limp-like. Now, what do? I put it on a circular disc, and I rotate that disc at very high speed on a rotator such as I had here. And then I trip off the chain or the loop. Now look what happens. There is the circular disc. Here's the chain around it. And I bring this up to a high speed. And I trip it off. Remember, the chain was a limp structure. And what does it do? It rolls away as a rigid, solid iron hoop, for reasons which I leave to you to explore. Now, since I am given to the physics of toys, I ask you to consider another interesting little thing concerned with rotational motion. Here is a little toy which can shoot a hoop. A hoop. I will not reveal any of the secrets, but there is a rubber band which can give rise to a torque to turn the hoop. And, well, notice, it was an accident, but that's all right. I'm going to shoot the hoop away. Question. You will see the hoop roll away, and then you will see the hoop roll back. Or have I said it correctly? Let me invite your attention to this enchanting little business. Watch it. There it is. Now, I'm going to do it again because I like it. And if I like it, that's reason enough to do it. Watch it. There it is. There it is. And I want to know what is going on. So you see, boys and girls and ladies and gentlemen, another bit of my philosophy here, my instructional philosophy. It is not always to answer the questions, but to raise some interesting dilemmas. Why things are so. Why things are so. Now, let me see what else we have here. I am not a cowboy, but the question arises. How is it that a cowboy can make a lariat or a lasso, L-A-S-S-O, often mispronounced lasso? How can a cowboy make the thing go in a circle, in a ring? Well, there it is. Notice the circular shape it took up. And the question arises, why is it circular? Interesting. Dilemma. A jug of water. Do you see again, ladies and gentlemen, and boys and girls, again some more of my philosophy. I use often the most plebeian and humble and simple and trivial things to demonstrate these wonderful properties of nature. How can I most quickly empty this jug? Watch it. There it is, and I thank you for giving attention to our business. This is the quickest way for the water to come out of the jug. How do you do, ladies and gentlemen, and boys and girls? I'm Julius Sumner Miller, and physics is my business. And our very special business today is the enchanting phenomena associated with things that roll, rolling things, hoops and spheres and discs and the like. Consider the following. I have here a board which I can use as an inclined plane by raising it higher or making it lower, and here is a block of wood. We all know that if I raise the plane high enough, there comes an angle, there's a little stickiness there comes an angle at which the block slides. Indeed, if I had a block twice as heavy, we would find, if we explored it experimentally, that the block twice as heavy slides at the same angle as the one block alone. And I'm going to write the mathematics of that for you so you can have something to think about. It says, the mathematics says, that mg sine of theta is equal to mu mg cosine of theta. And from the algebra, you know, I can divide out the m, so the mass of the body does not matter when things slide. Now, when we consider things that roll, another interesting and enchanting detail arises. Here I have a disc of wood wherein we see the mass uniformly distributed. There is some everywhere with respect, say, to a central geometric axis. Here we have a hoop. The hoop has another property. All the mass of the hoop with respect to a central geometric axis is in the periphery, in the edge. So now, this brass hoop and this wooden disc have the same mass, but their distribution of mass is different. If then I put them at the top of the plane, since we see also they have the same diameter, the same radius, the same surface contact, which indeed doesn't matter a bit, we ask, how do they roll when I let them go? Do they roll together, that is, keeping neck and neck? Or does the disc win, or does the hoop win? And I'm going to show you how this does indeed come out. Watch it. And so we see the disc winning. Now I'm going to roll another disc. Here is a disc, aluminum, much smaller than the hoop, and I'm going to roll these together. This is a disc and still the hoop. And the disc again wins. Now I'm going to roll these two discs together. Small disc, big disc. It will be a little difficult to check this, but if our provisions for nature were of an adequate sort, I could show you the following phenomena. Watch it. Did we not, I must go further, did we not see this disc beat this hoop? Did we not see this disc beat this hoop? Let me take another hoop. Here is a hoop. Well, it's a long one with a long axis, but it's a hoop. And here is a disc. Watch now. This disc is beating this hoop. This disc is beating this hoop. Here is another hoop and another disc. This disc is beating this hoop. Let me take another hoop and a disc. This disc is beating this hoop. And what am I getting at? I'm getting at a most astonishing discovery. First, if I rolled all the discs in the world, I would find that all discs roll alike. Alike. I would find that all hoops roll alike. Little hoops, big hoops, fat hoops, skinny hoops, they all roll alike. Big discs, skinny discs, here is a disc, here is a disc. Now, because it has a long axis, we call it a cylinder, but I'm going to show you that that disc behaves the same with this hoop as other discs did. Watch it. And so I'm going to tell you another secret. All discs roll alike, all hoops roll alike. Now all discs beat all hoops. All discs. So now somebody says, Professor, you have not lived long enough to roll all the discs and all the hoops in the world, so how do you know that? Indeed, no one has ever rolled all the discs and all the hoops in the world. But I have rolled discs and hoops in America, in Canada, in Africa, in Australia, and always I find that all the discs I rolled roll alike, and all the hoops I rolled rolled alike, and all the discs I rolled beat all the hoops. Now, I'm going to give you the argument, the proof that all discs roll alike. Here it is. I'm going to write some mathematics. FR equals I alpha. And somebody says, what does that say, Miller? I'll tell you what it says. It tells me that if I put the right stuff in there for the force and the radius and the mass distribution of the body called the moment of inertia, I get an expression for the angular change, the angular acceleration. Or I could write the potential energy at the top of the plane is equal to the kinetic energy of translation plus the kinetic energy of rotation. What I am getting at here, boys and girls and ladies and gentlemen, is this, that a proper understanding of the affairs of nature lies in the mathematics which describes it, because words are very weak. Now, I said that all discs roll alike and all hoops roll alike. The question now is, how about some spheres? Well, here is a big sphere, here is a middle-sized sphere, and here is a baby sphere. And if the board met my requirements and I let them all go at the same time, they would keep equal separation, and I would make a further announcement. The further announcement, all spheres roll alike. Now, the hoops that I spoke of have to be very proper hoops with all the mass in the periphery. The discs must be very proper discs, all the mass uniformly distributed, and the spheres must be very proper spheres, uniform mass distribution. The only question that remains now is this. If a disc beats a hoop, and all discs beat all hoops, and all spheres roll alike, how do spheres and discs and hoops roll? Well, we know this beats this, and so the question is, where does this come in the game? Well, look here. If I roll the sphere, excuse me, if I roll the sphere with the hoop, and something wins, watch it, I assure you that the sphere wins. You now know that spheres beat hoops, but what do spheres do with discs? Oh, a wonderful thing. Watch it. We have a little trouble with this board, but that's another piece of evidence that when you deal with nature, spelled with a capital N, you must make such requirements as she demands. A little difficult to show it, the hazards of experiment, but I'm going to tell you, all spheres beat all discs. So if all spheres beat all discs, then all discs beat all hoops. If we let them go at the top of the track, the spheres always win, the discs come second, and the hoops last. Now I said that all discs roll alike. Here are two discs, and without revealing their nature, I'm going to roll them. Watch now. I'm going to roll them. Oh, one is winning, and yet they look like two uniform discs. No, they are not. So I have to reveal the secret. This disc, this one here, has some weights at the center. This one has the same weights on the edge. So you see, when the mass is farther from the geometric axis, the motion is slower. And I'm going to show you that. Here's the one with the weights lodged in the periphery, and here is the one with the weights lodged near the center. Watch now the motion. There it is. And so we uncover a most remarkable thing. And I would invite you, wherever you go in the world, find a disc and a sphere and a hoop and roll them and see if what I say is not true. Now, concerning rolling bodies further. You all know what a yo-yo is. Here is a yo-yo. But before I go to that, I want to remind you, the only reason this body can roll, is that there is friction between it and the inclined plane. Without friction, there can be no rolling. Consider the behavior of your automobile wheels on a very icy surface. They cannot roll. Accordingly, in the playing with a yo-yo, what do we find? What is a yo-yo? A yo-yo is a disc with a central axis around which is wound a string. So this is a body rolling on an inclined plane, which is usually vertical. Watch it. Oh, now do you see? There is not enough friction there for the gripping to climb back. Watch it, and I hope it doesn't work properly, because that will prove the point I wish to make. Oh, notice. Oh, there it is, there it is. It is not climbing back. If the friction is adequate, a very enchanting thing arises. Here is a yo-yo, a big one, with a small central shaft, and I'm going to let it go. And the point I wish to make here is this. When it gets to the bottom of its route, there is felt a sudden jerk, yank, pull impulsively in the string, and the thing changes direction and comes back up. How far can it come up? Never to the height from which it was released. Why? Because the energy of a system always goes toward less. Watch it. Well, we had a little trouble with the twisting of the string. One more business regarding rolling things. And I invite your attention to this because it is a very powerful question. Supposing I had a wheel rolling without slipping on a surface, and I considered some point on the wheel, and I ask you, as the wheel rolls, what kind of a path does this point make? What kind? Well, some people draw something like this. All kinds of twisty matters. I'm going to show you, because it is a very important business. The point on the wheel does this. And that curve is a cycloid about which you should read, because it has stirred mathematicians for hundreds of years. And I thank you for your attention.
You're watching WNEO Youngstown and WEAO Akron.
How do you do, ladies and gentlemen, and boys and girls? I'm Julius Sumner Miller, and physics is my business. And our business today is the classic adventure of Archimedes about the 3rd century BC, with some wondrous things to report. First, consider a body, a lead weight, which I hang on a spring scale, and the scale reads so much. I am not interested in what it reads, but it reads the weight of the body. Now let me submerge this body in a vessel of water, and we see a remarkable thing, a very remarkable thing. As I submerge it, the scale reads less and less and less, and I urge you to see that the weight is not resting on the bottom of the vessel of water. Accordingly, when I submerged the body, the water pushed up on it, provided a buoyant force, as we say, which Archimedes discovered in his classical bathtub experiment. Eureka, eureka, I have found it. Now, how much is the push up of the water on a body submerged? Archimedes said it this way. When a body is submerged in a fluid, that's either a gas or a liquid, we're talking liquids here. When a body is submerged in a liquid, it is buoyed up by a force equal to the weight of the liquid displaced. Now, I can prove that. Here I have a vessel which has an overflow spout, and I'm going to put a little water in it to be sure the water is up to the level of the spout. There it is. It's coming out there somewhat. And now I'll wait until it stops. The water is up to the level of the spout in this chamber. Now, I'm going to get rid of that water. Now, what am I going to do? I'm going to submerge this body in that chamber of water, and as anyone in his right mind would recognize and attest, will not some water be pushed out? Indeed, and I'm going to push some water out and catch it in that little bucket. Watch it now. And of course, again, the scale will read less, but I'm not interested in that this time. I'm interested in the water that gets pushed out. Watch it now. And I'll wait till all that's going to be pushed out is pushed out. That's good enough. Now, what would I do with these adventures? Well, first I would have noticed how much less the scale read when the body was submerged in the liquid. Suppose it read less by 10 grams. Then I weigh this water in this bucket. And what would the water in this bucket weigh? 10 grams, meaning that the body was buoyed up by a force equal to the weight of the water this body displaced. Archimedes' principle. Fantastic. Now, I said that the water pushes up. I'm going to prove that. Indeed, you should recognize it already from your adventures by the sea. When you walk into the ocean, do you not discover that the deeper you go, the less push your feet have on the earth below? Because the water is buoying you up more and more, the deeper submerged your body becomes. Here I have a glass and a hole in the very bottom, and I'm going to push the glass down. The evidence that the water pushes up will be witnessed by the water coming up into that hole. Watch it. There it is. There it is. And I say the water pushes up. I'm going to prove that in another way. Here is a glass tube and a plate on a string. And I'm going to put the string through this glass tube. And now I'm holding the string in hand. And obviously, since the plate has weight, if I let go of the string, the plate will fall down. Watch it. Well, of course, says anyone who's watching. Doesn't that professor know that if you let go of the plate, it'll fall down? Of course it'll fall down. Now I'm going to prove again that the water pushes up. Why, how? I'm going to put this into the water, and instantly I make connection with the water, I'm going to let go of the string. When I let go of the string out here, the plate fell off. The plate will not fall off in there. Watch it. There it is. And you see water rushing into the inner cylinder, climbing higher and higher. And everybody says, well, when it gets the same height inside the vessel as outside the vessel, then the plate will fall off. And I'm going to leave that for you to think about. But now, my new adventure. Archimedes bucket and cylinder. I have here a little bucket, very nicely formed, and a solid cylinder which fits it exactly, And here's what I'm going to do. I'm going to balance this bucket. I'm going to balance that bucket with the cylinder below. Let me see if I can represent that. Here is the cylinder below. And remember, that solid cylinder fits that bucket exactly. And I'm going to balance this with some weights over here. Put the beam balance in equilibrium. Then what am I going to do? I'm going to come up underneath with a vessel of water in this fashion. Vessel of water, so that I submerge the solid cylinder. The equilibrium in the balance will be destroyed, as we might say, because why? The water here is pushing the cylinder up. How much is it pushing the cylinder up? It is pushing the cylinder up with a force equal to the weight of that water displaced. And how much water is displaced? The volume of the cylinder. And how much is the volume of the cylinder? The volume of the cup. Accordingly, with the equilibrium destroyed because there is a lift or buoyant force here, I am now going to pour some water into this little bucket. Water, 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 water. Oh, ho. When this bucket gets full, what will we see? An absolutely enchanting thing. We will see the equilibrium restored. Now I have such a bucket and cylinder. There's the cylinder, there's the bucket, and I have put it in equilibrium on the scale. Now I'm going to bring up this water and submerge the lower solid cylinder. I hope you see that the equilibrium has been destroyed. The balance is no longer in balance. Oh, I came up too high. Now I am going to fill the little bucket. I'm having a little trouble here being steady. I'm going to fill the little bucket, and the equilibrium, which does not now exist in the scale reading, will be restored. Watch me now. Oh, I filled it over much, and there's a very high meniscus. So, Archimedes bucket and cylinder. The proof is very beautiful. A body is buoyed up by a force equal to the weight of the water displaced. Now, regarding buoyant forces and bodies that sink and bodies that float, here is a vessel of water and here's a piece of wood. Floats. Here is another piece of wood. Wood, water. Heavier than water. Lignum vitae. Here is a piece of wood. Heavier than water. So there are woods that sink and woods that float, their densities being less or more than that of water. Now, regarding bodies submerged in liquids, I have here something absolutely enchanting. Here is a vessel of water in which I'm going to put a wooden ball. There. It sinks about, I don't know, 5/8 or something like that. Now, here is a vessel of mercury. Vessel of mercury. I'm going to put the ball in the vessel of mercury. Watch it. It doesn't sink at all, hardly. Hardly. It rides on the very surface. But that's wood. Very light. How about steel? Oh-ho! You know that the specific gravity of steel is about 7 or 8. The specific gravity of water is 1. You know that steel sinks in water. Watch it. Sinks to the bottom. By the way, I say steel sinks in water. On an earlier program on surface tension and the strange behavior of the free surfaces of liquids, I showed in a demonstration where I float a steel needle on water, so steel can be made to float on water. But how about the steel ball in the mercury? Watch it. Oh, this is something. There it is. There it is. The steel floating on the mercury. This is a marvelous thing. Let me use a larger steel sphere, because this is enchanting to see. There it is. Steel floating in mercury. Now, talking about Archimedes leads me to show you a classic mosaic. You remember that Archimedes defended the city of Syracuse when it was attacked by the Romans under the general Marcellus. And then Archimedes was put to death by a Roman soldier who ran upon him while he was doing a demonstration in the sand. So here is that mosaic, which I hope you will see. There is the Roman soldier urging Archimedes, "Come to my general Marcellus." And Archimedes begged him, "Let me finish first my demonstration." And here is another monument to Archimedes, which shows him holding a mirror. This is a little glossy and hard to see. Holding a mirror with which, you remember, he set fire to the enemy ships far from shore. So, what have we discovered here? The remarkable principle of Archimedes that a body submerged in a liquid is buoyed up by a force equal to the weight of the liquid displaced. Now, Archimedes, as you know, apart from being a natural philosopher of the first magnitude, was also a mathematician. And I want to tell you quickly about some things he discovered of a mathematical nature, because they are enchanting. And here they are. Here I have a right circular cylinder, and here I have a right circular cone, and here I have a sphere. They are the same altitude and the same radius. And what did Archimedes discover? He discovered, by playing with these, filling them now in turn with sand, that the volumes were uniquely related in the ratio of 1 to 2 to 3. I'll leave it to you to discover how that ratio goes with respect to the bodies. Now, in his later years, having made many discoveries of great moment and significance, he was asked what he viewed as his greatest. And he referred to this, the ratio of the volumes of the cylinder to the cone to the sphere, and asked that when he dies, such a matter be put atop his tomb, which shows a cylinder, a sphere circumscribed by a cylinder. So here is a sphere about which is circumscribed a cylinder. And this was put on top of Archimedes' tomb, buried near Syracuse. Where are we then in this dialogue? Archimedes, 3rd century BC, who must certainly rank with Newton of the 17th century and Einstein of the 20th. So next time you go to the sea to bathe, remember Archimedes. And when indeed you take a bath in your bathtub, and you submerge yourself in the water, and the water rises, remember the affairs here, which revealed that beautiful fact, which we use abundantly, because after all, this is why ships can sail on the sea, and submarines under the sea, and airplanes above the sea. And I thank you for your attention. How do you do, ladies and gentlemen, and boys and girls? I'm Julius Sumner Miller, and physics is my business. And our very special business today is the work of the young Frenchman Blaise Pascal, a genius of the 17th century, who died at an early age, indeed at 39, but left enough for us to contemplate for a lifetime. And I urge you to read his life, written by his sister, La Vie de Blaise Pascal, the life of Blaise Pascal. Indeed, at the age of 12, he happened one day to strike a dinner plate belonging to his mother, and it rang out, and he was thus led to write a definitive paper on vibrating bodies. I urge you to go read about him. Now, one of the principal things he had concern with was the property of liquids and of fluids, and raised a very interesting problem. Consider, let us get a picture of him. Here he is, just some few years before his death. Blaise Pascal, a genius of the 17th century. Consider the following. Supposing I have a vessel shaped like that, another one with the same base shaped like that, and another one with the same base shaped like that. Three identical vessels, that is, the bases identical, and now I fill them with water to the very same level. Water, water, water. Question, on the bottom of which vessel do we have the greatest force? Answer. Discussion. Most water here, most mass of water, most weight of water. The bottom here supports all the water bounded by those vertical lines. The bottom here supports the water bounded by those vertical lines. The bottom here supports the water bounded by those vertical lines. Well, says somebody, I see water in here and water in here. What holds that water up? Answer, the sides. Then somebody says, there's no water in here and no water in here, and yet the push on the bottom is the same. Answer, yes. Reason, the walls push in with a force which compensates for the water which is not there. And I'm going to show you this with a wonderful experiment. Here it is. Here it is. Here is a narrow-walled vessel, and I'm going to fill it to a certain level by raising a chamber of water. Here comes the water, here comes the water, there comes the water. Oh, hold it, right there. I'll get the water level in here proper as measured by the position of this marker. And if we read the scale, it reads about 43 or 4. Now I'm going to let the water run out of there and replace this vessel by a very big one, quite like the middle vessel that I drew on the board. And I hope you see that this vessel is vastly bigger than this one, but they have the same bases. They have the same base. I'm going to screw that on there, if I can do it here. There we go. And now I'm going to raise the water in here to the same level as in the other one, and I hope you will see that the gauges read the same. There's always a little trouble with the linkage system in such a mechanism, so there may be a little trouble, but I'm bringing the water up to the same level. Since the sides are flared out, the rate of growth of depth is less, but there we have it. Oh, I've exceeded the level a little bit. I'll come down a little. I'll come down a little. And I think that's evidence enough that the readings are identical. The readings are identical. Amazing piece of business. Consider another consequence of Pascal's work. Supposing I have a little chamber here connected to a big chamber here, and I put a piston in this chamber and a piston in this chamber, and this is filled, of course, with some incompressible fluid, oil or water. You are aware that if I push down on this piston, the water goes up there and lifts that piston. This is an hydraulic press. If indeed I make this a compound machine by attaching a lever in this manner, and I apply a force here, I can pump the liquid from here down and lift an enormous load. Indeed. If this piston is very small compared with that one, I can multiply the force I apply here, depending upon the length of this lever, thousands of fold. And I'm going to show you that. Here I have such a system. Here I have such a system. A little piston right here, and a big piston right there, and here is a block of wood. Here is a block of wood. And I say it takes about a ton of force to break that wood, and I can't do it with the unaided hand, but let me put it in there. I made a little mistake. I have to come down a bit. Watch it now. Watch. I am going to deliver. And here is what I wish you all to see. That with ever so tiny a force applied out here, with my little finger, I can produce a force of about 1 ton at the middle of the board above this piston. Watch it now. Watch the scale. Oh, well, this board broke at about ½ a ton. Now, you know very well that I could not exert a force of ½ a ton with my naked hands. Here is a board, a piece of 2 by 2. I would say that it will take about 2 tons to break this. About 2 tons. Now, watch it. This is fantastic. Applying Pascal's view that the liquid is incompressible and any small force applied here is felt without loss in all parts of the machine. Watch it now. There it reads 1.5 tons. There, it fractured at something around 1.5 tons. And I say that is fantastic. Oh, staggering, staggering. The forces which we can impress here. Now, I could show you another experiment with that hydraulic press. Here is a spring. I will not pursue the adventure, but this spring has an enormous modulus, meaning that it takes extraordinary forces to squeeze it together. More than 2 tons, in fact. I couldn't do it with the naked hand, but there I could do it very easily. Let us consider another consequence of Pascal. Here's one of very great usefulness to the human race. Here is a hypodermic needle. Question, why is the needle sharp, very pointed? Answer, for the same reason that you wear snowshoes to cross deep snow. You spread your force out over a large area, so the pressure, which is the force per unit area, is very high here in the needle. For example, ladies with high heels. A little girl weighing 100 pounds can leave more impression on an earth road than an elephant. Imagine that. Why? Because her weight is on so small an area. So here we have it. I push with a force of 10 pounds with my thumb. The hypodermic needle has a pointed area of about 1/1000th of a square inch. The pressure is 10,000 pounds per square inch. Fantastic. Fantastic. Consider another one. This is beautiful. Here I have a flask filled with colored water, 1-hole stopper in a glass tube. And I call your attention to the level of the water right here. I hope you can see it. The level of the water right there. A little difficult. There, that's very good. Beautiful. Now, what am I going to do? I'm going to squeeze on the wide sides of the glass. And we see an astonishing thing. Watch the level of the water. Watch it. There it goes up. Suggesting 2 things, that the glass is very elastic and the water highly incompressible. Another adventure with the same thing. Let me turn the glass sidewise. Let me squeeze on the narrow sides. Question, what will the level of the liquid do? Answer, when I squeeze the wide sides, I deformed them inward, diminished the volume of the vessel, and up went the liquid. When I squeeze them on the wide sides, will I not bulge out the wide walls, and will not the liquid fall? Watch it. There it is. It goes down. Another adventure which you can pursue, the Cartesian diver. Here I have a little creature in the shape of a man in which we have put some water, and he floats at a certain position. There is some air above the column of water. There is some air in him. What am I going to do? I'm going to push down on that rubber sheet here. That force by Pascal is communicated without loss to all parts. The water in here feels it. The water in him feels it. The air inside of him feels it. And because the air is compressible, it gets compressed, more water goes in, and he goes down. So you see, it is not me pushing that pushes him down. It is this sequence of actions. Watch it. There it is. I love that little business. And, whoop, I can stop him where I want. Since they are differently loaded, they ride at different positions. Now you can make one very easily. You don't need such a thing as that. A little medicine vial would do, such as little pills and the like come in, and here it is. Here it is. There it is. Like a submarine, in fact, exactly how a submarine works. I release the force or the pressure, and up he comes. Consider another consequence. Let's go over here, back to this table, because there are some enchanting things. Here is an experiment which we could do, but we will not. We will consider it a virtual demonstration. Here is a flask, filled completely with water, completely, with a tight-fitting stopper. Liquids, I say, are incompressible. Conclusion, I can deliver a sharp, impulsive blow to that stopper. So, that force would be felt in all parts of this chamber, and it would burst into a million bits, and the water and glass scatter. Enormous. Why? Because Pascal said any force delivered to a liquid is communicated without diminution, without any lessening, to all parts. Another one of the same kind. Here is a wooden block with some nails in it, and here is a flask. Unfortunately, this flask has a bubble in it, which I think you can see. And bubbles of air are highly compressible. I cannot, therefore, do what I want to do. But supposing I fill the flask completely full of water, I could then use it with absolute immunity to drive that nail into that block. Why? Because water is highly incompressible, and the vessel would feel nothing. This would act like a solid hammer. Another consequence of Pascal and of Torricelli. Beautiful thing. I have a can here filled with water, and I hope you can see on a close shot that there is a hole in that can, and yet the water does not come out. And I say, that's fantastic. I'm going to pull out the stopper. Watch it. I'll give you evidence that there's water there. There it is. I put the stopper back in. The water has ceased running out. Question, what's holding it in? Obviously, atmospheric pressure. Question, very important. How tall a can could I use to do this? Answer, 34 feet. Isn't that fantastic? Fantastic. Now, one more demonstration. One more. I have here a U-tube. A U-tube. That's a tube shaped in the form of a U. Mercury in the bottom part. Water colored above it. And you see there is a difference in levels in the mercury columns. What will be the ratio of the water level to the difference in the mercury levels? Answer, 13.6, which is the specific gravity of mercury. And I invite you to do this experiment and wish you good fortune. How do you do, ladies and gentlemen, and boys and girls? I am Julius Sumner Miller, and physics is my business. And our very special business today is the subject of simple machines. Simple machines. Now, when you study these matters in school, it is usually said that these are the 6 simple machines. The lever, or as some pronounce it, the lever, the inclined plane, the wheel and axle, the screw, the wedge, and the pulley. And I wish in this program to show that really all of these reduce to only 2, the lever and the inclined plane. And what is better for us to contemplate is the following, that all of the things I will have to deal with here today are the most plebeian and simple and homely and commonplace. And my purpose is essentially this, that when you pick up your fork and knife to eat your dinner, I hope you would recognize that you are using some levers. Indeed, the sharpened blade of the knife is an inclined plane in addition to the tool itself being a lever or lever. And how about the prongs of the fork? The prongs of the fork are usually sharpened a little bit, so they are wedges, and wedges are inclined planes. So let us go at random to some of the things we have here, and you will see exactly what I mean. Consider, for example, the following. Here is a block of wood in which I have already lodged some bolts and screws and other things. Here is a screw, and I'm going to attempt to lodge it further into the wood with a tiny screwdriver. A tiny screwdriver. No success. Why? Well, let us look at what really happens. The handle of the screwdriver I have enlarged, looks like that, and I apply a force this way and a force that way, so that I turn it about a central axis, and these 2 forces, equal and oppositely directed and parallel, are said to be a couple, C-O-U-P-L-E. You see a couple of forces acting in this way. Now, the small screwdriver had too small a radius. So what do? I use a big screwdriver, and the same force will accomplish my purpose very readily, as you will see. Here is a big one. And the handle, of course, is very much bigger, so that the torque, or the turning effect of my force, is very much increased. There it is. Beautifully accomplished. Consider now, I remark that a threaded cylinder, which we call a screw, is really an inclined plane. And I hope you see the inclined planeness in this threaded shaft. I'm going to prove to you that it's an inclined plane. Here I have an inclined plane cut out of paper, and it goes uphill to my left. I'm going to wrap this around a cylinder, and I hope you see that what I will get out of it is this. Here is the cylinder, and I wrap the inclined plane around, and I get a threaded shaft, which is a screw. Now watch this. Here, I'm going to wrap it around. Let me finish it here first. And there you will see the inclined threads. Now, I have wrapped this one around so that the threads go like that, which is a left-handed screw. I have cut the other one so that when I wrap it around, it gives me, I hope, yes, let me turn it over. No, there. Notice, I'm a little twisted up here. Well, notice, I'm glad I'm twisted up because this suggests that even professors of physics can get a little bewildered. I know where I made the mistake. One of these I have to turn over and use the mirror image, and then it will give me a right-handed screw. Now, this business of left-handed thread and right-handed thread, very important. Illustration. Oxygen tanks used to take care of sick people are right-handed threaded. Nitrogen tanks, on the other hand, I believe, are left-handed threaded, for the very reason that then nitrogen could not be inadvertently and accidentally fed to a patient who should be getting oxygen. See, very important idea. Let's look at another one. Here is a bottle with a screw cap, and the housewife finds that she cannot undo it because it is too firmly fixed. What does she do? Answer. Provide herself with a lever and a notched jaw, which is essentially an inclined plane. And then she puts it on there, and ever so gently, there it is. So I say that for little bottles with small screw caps, you have a small Stilson wrench, and for medium bottles, a bigger Stilson wrench, and for very big bottles, a very big Stilson wrench. And any well-equipped household, I think, should have at least 3 Stilson wrenches. Consider, for the housewives and the boys and girls and the teachers, here is a grater. Now, what is a grater? A grater, well, a grater, you grate with a grater. There it is. And I say a grater is an inclined plane. Very clearly an inclined plane. How about a wedge? A wedge. A wedge is clearly an inclined plane. Consider the following. Here is a railroad spike. Indeed, it is pointed. Quite like nails are pointed. Why? They are inclined planes, and the advance into the railroad tie is more easily accomplished because this is an inclined plane. Let's go to an ordinary hammer. Here is a nail that I've lodged in here. A lot to say about this. Let me use the hammer as a lever. Not much success. I improve its mechanical advantage by providing a block under the head, and there. And now what must I say? What must I say? Very important. What do I feel when I feel this nail? Very hot. Friction develops heat, and friction is a dissipative force, always arising when work is done, and about which we spend fortunes to eliminate. Very important. But remember, if we could accomplish the elimination of friction, no motion whatsoever would be possible. A very terrible thing to contemplate. Here I have another one in front of me. How about a nutcracker, a lever? What happens? I put the nut in here, and then easily accomplished, effortlessly. Here's one for the housewives and the boys and girls and the mothers and fathers and the school teachers. A broom. A broom, I regret to say, is a lever. And next time you sweep the house, I wish you would have some regard for Archimedes of the 3rd century B.C. And I'm going to show you how the lever can be used in an enchanting way. The usual way is what? We hold it there and push here, push here, push here. The fulcrum here and the force there and the load down there. It can be used in another way. Watch me. I'm going to have the fulcrum here, and I'm going to push it here. Not too handsome a way to use a broom, but it can be used as another class lever. More on the same. If indeed the subject is getting, let us say, monotonous, it should not be. All these things are levers. Here is a piece of metal. Here a little pair of metal clippers. I have difficulty. Why? Not enough lever arm. Not enough lever arm. A larger shears, effortlessly. There it is, like cutting butter. Or consider a file. What is a file? A file is a succession of inclined planes. And regarding a file, I hope sometime you will be able to go to Milan, Italy. And in the Museum de Leonardo da Vinci, there are many of Leonardo's devices, and one of them is his file maker. And when I was there last, I used it and made, indeed, some scratches on a file. How about a meat grinder? Oh, nobody uses a meat grinder much these days because it's done for you. But if you will look inside, you will see that that is an inclined plane. Beautiful there. The camera catches it nicely. Here it is. Here's one of the cutting tools from inside, and you see it is an inclined plane. How about an egg beater? An egg beater. An egg beater is not a simple machine. An egg beater is a compound machine made up of a lever, the handle, and some geared wheels. And what do? We turn the geared wheel. There is a certain number of notches on the big wheel and a certain number there. The handle is so long, and so we speak of the mechanical advantage of a simple machine. Meaning what? How many times is the force multiplied when we apply a force? If, for example, with a force of 1 pound I can lift a ton, then the mechanical advantage is 2,000. Let me go further. Here is an interesting thing. Pulleys. Pulleys. Now it is very important that I say something about pulleys. When students and boys and girls study pulleys, it is usually said that to find the mechanical advantage of a pulley system, you count the number of ropes supporting the load. Now, I should say that this is not a good thing to do. It sometimes leads to the right answer, but often the right answer is gotten by physically wrong means. And this is a very important philosophy to remember. Getting the right answer is the least important of your endeavors. What must be right is the logical, analytical reasoning that leads to it. So I would urge you to study pulleys and learn how to find the mechanical advantage without counting the number of ropes. Here is a pulley system made up of 2 blocks with 3 sheaves each, or 3 pulleys each, rather, and I can lift an enormous force by the application of a small one. Notice, friction is not playing an adequate role, and so the system unwinds. And when I talk about pulleys, what name in history must come to my mind? Answer, Archimedes, because you remember he designed all kinds of machines of war in order to protect the city of Syracuse against the invasion by the Romans. And I would urge you to read the story of this great adventure as recorded by Plutarch, The Siege of Syracuse by Marcellus, the Roman general. Where am I now? Where am I? Oh, let us take some ordinary cutting pliers. What is a cutting plier? Well, we say it in the plural, pliers, wire cutters. First, it's a lever. Secondly, it's an inclined plane because the cutting jaws are inclined for sharpness. And ever so effortlessly, I cut a wire. And so, ladies and gentlemen, and boys and girls, we come to the end of this program, indeed, to the end of this 15th program, and what has been my singular ambition throughout the series. It has been just this: not to teach you any physics, not to assign any lessons or any problems, but rather to point up the beauty and the drama in all of this and to excite your enthusiasm and your curiosity, for these are the foundations which will lead to your better understanding. Now, what have we done? What do physicists do? What is physics? What is science? That's an all-embracive term. Science, of course, is what scientists do. Physics is what physicists do. And what do physicists do? Physicists explore how nature behaves. And I urge you to spell that nature with a capital N. So as you go about your daily affairs, your school days, your days at home, your playing hours, I would urge you to have a regard for the things all around you, for they are filled with beauty and drama. And seeing how nature behaves will give you a full life. And I thank you for listening. How do you do, ladies and gentlemen, and boys and girls? I am Julius Sumner Miller, and physics is my business. And our very special business today is the subject of heat and temperature. Now, to refresh your mind on my philosophy, as in the first series, which we did on mechanics, I must say the following. This is not a lecture in physics. I propose, rather, to show an array of demonstrations, dramatic and exciting, in the subject before us, with the purpose, for the purpose, of stirring your curiosity, arousing your enthusiasm, pointing up the beauty and drama of these things, so that each one of these demonstrations will invite you irresistibly to go and do it yourself with your teachers, to see the beauty and the excitement that can be uncovered in these things. So, this is not strictly a lesson in physics, but rather a lesson in the excitement and drama in the subject of heat and temperature. Now, I would remind you, heat and temperature. For this and subsequent lessons, it is absolutely essential that the difference in these words be understood. And for this purpose, now, some demonstrations. Consider first the following. I have here a glass tube in which I have put a little mercury, and on top of the glass tube, some little bits of chipped glass, little bits of chipped glass. Then I have drawn the tube down by heating the glass, pumped out some of the air, and then sealed it off. So we have here a tube with some mercury and some little glass and largely empty space in here. Now what am I going to do? I am going to heat this test tube. Heat it. This will be my symbol for adding heat to a system, much like a candle. And I have a warm feeling for candles because my beloved friend Michael Faraday gave 6 one-hour lectures at the Royal Institution on a candle. And about Faraday, I will one day speak when I do some programs on electricity and magnetism. So I'm going to heat this. And what will we see? We will see after a time the little bits of glass dancing about very energetically. So I am telling you that heat is a mode of motion. Let us do that. Here is the burner, and I am doing this with some caution because we could explode the thing and have some disaster. Now I am heating it. I am heating it. I am heating it. I am heating it. Wait a minute, I think I'll take another one. I see a little soot on the bottom of that other one, which may interfere with our operations. I am heating it. I am adding heat energy to it. Ah, there we are. There we are. Look at that agitation. Heat is a mode of motion. Heat energy. I have communicated thermal energy to the system. Now, who was the first one to tell us, to suggest that heat is a mode of motion? I am led irresistibly to show you a picture of one of those rascals known as the Bernoullis. And I have to see, oh, that's the camera. That's the camera I'm playing to. This is one of the Bernoullis. And you may remember on my programs on mechanics, I made reference to the Bernoullis and did a program on Bernoulli. They were a family of over 100, all geniuses, not one an ordinary man. Now more regarding heat and temperature. Let's get over here and consider the following. Here I have 2 beakers. This beaker has a little water in it, and this beaker has much water in it. Now, I tell you that if I put thermometers in these, that they read the same. Therefore, I tell you that they are at the same temperature. Same temperature. But is there not much more stuff here in a state of agitation than in here? Accordingly, they do not have, let me write that, unequal heat. Same temperature, but different amounts of heat. Now let's look at another pair. Here are two beakers, one with a little water, one with much water. I assert that if I put the thermometers here and wait for the time to elapse to get a proper reading, I tell you that these are vastly different in temperature. This little one has a high temperature, and this one has a low temperature. And what am I prepared to tell you regarding these? From what I have said, heat is a mode of motion. There is much more stuff in motion here than here, but here, the temperature being higher, the motion is much faster. So I could say that these have the same heat energy. The same heat energy. I hope you are getting the idea of the distinction between heat and temperature. Let me try it another way. Consider the following. Consider this. I have here some spheres of different materials. Brass, lead, aluminum, iron, and so on. Now, this experiment that I'm going to do, I call virtual. Virtual. As distinguished from some demonstrations which I do, which we call real. Real ones are those I really do, and virtual ones are ones we will have to imagine. Now, I have often said that imagination is a very necessary ingredient of your life and work. So you will imagine that I have put these spheres into a beaker, and I have added some water, and I have put it on a tripod, and I have put some heat energy under it. Here it is. There is the beaker. There are the spheres in there. There's some water in there, and I apply some heat energy. And I cook them, as I would say, for a long time. Long time I cook them. Boil the water and boil the water. Will you not agree that after a time they will all be at the same temperature? The same temperature. Now what do I propose to do? I propose to take them out of the beaker with a forceps and put them one by one on a block of paraffin. And what will we observe? An astonishing thing. We will observe that they sink to different depths in the paraffin, meaning, of course, that they possessed different amounts of heat energy. Different amounts of heat energy. Different thermal energy. Different heat energy. Why? They were able to do different amounts of work. Consider the same thing viewed another way. These spheres are all steel. I heated them to the same temperature in such a beaker of water. And what do we discover? That even though they are at the same temperature, they have melted different amounts of paraffin and therefore were able to do different amounts of work. I hope you see, boys and girls and ladies and gentlemen, that I have been using the words heat and energy synonymously because they are one and the same thing. Heat is a form of energy. Now I have suggested same temperature, different heat. Consider a plebeian little adventure. Here I have two potatoes, an enormously large one and a small one. Let us put them in the oven and bake them. You will agree that after some proper elapse of time, they are at what? They are at the same temperature. But now you know that this one has vastly more heat energy in it than this one. Same temperature, different heat energy. Or consider another. We wish to show again that heat is a mode of motion. I have here two beakers. This one, I say, has cold water in it, so I report to you. And this one has hot water in it, so I report. Now, mark you, I said that this is cold and that's hot, and I reported to you with my hands. That is a very unreliable report, as I shall show you in a subsequent demonstration. But what do I want to do here? I am going to drop a little food coloring in this one, and we will see the rate at which it diffuses. Then I'm going to drop a little food coloring in this one, and we will see the rate at which it diffuses there. Here we agree. Same amounts of water, very nearly. Oh, I stole a little, so I'll put it back. There we are. Since we want to do the experiment with some reliability and integrity, we will see the diffusion here, I hope, much more rapid than in the cold. Watch it. Watch it. There you see it going down so fast. I think it's going faster in this one. I do think it's going faster. And hence I have shown you that there is much more agitation in the water here than in there. To sum it up in a simpler phrase, what we mean by the temperature of a system is this. What is the average kinetic energy of the little elemental parts? The average kinetic energy, 1/2 mv squared, and I put a bar over the V to mean average. What is the average kinetic energy? Now, if we take all the kinetic energies of the little particles that are in motion and sum them up, that's the Greek letter sigma, which you will encounter when you study the calculus, which means you add up all the 1/2 mv squares, and you get the amount of energy in the system. Consider another. Look at this. Very dramatic as a virtual demonstration. Here I have a beaker of ice. If I put a thermometer in that beaker of ice, you know that after a time, the thermometer will read 0 degrees centigrade. The ice is not supercooled. Accordingly, the thermal energy in this system is so much. The temperature is so much. Now let me apply some heat under here. Add some thermal energy. I am adding heat energy to the system. We see some of the ice melt, but a most remarkable thing is witnessed. Namely what? That there is no change in the temperature. So we have had change of state, but no change in temperature. And about this, I shall speak on another program. Coming back to the unreliability, 3 beakers, cold, medium, hot. I put my hand so, this one feels cold, that one feels hot. I put them here, and I cannot tell you which is which, suggesting what? That the physiological determination of heat and temperature is most unreliable. So, I thank you for listening to this adventure, and we shall return another day.